Okay, thanks again. So yeah, this is the state of our qubit, and for now, these coefficients, you can just imagine them to be some sort of real number. So when we end up measuring our state, this is just one more rule that we're going to have to get used to. You're going to get into your 0 or 1 state probabilistically. So it's not going to be deterministic like it is in classical computing, but instead, we're going to have these rules. So the probability of getting a 0 is the coefficient of the 0 squared, and the probability of getting the 1 is the coefficient of the 1 squared. So we'll see some examples of this later, but does this make sense to everyone right now? Just some pretty simple rules to like square the number, you get the probability. So as a first question, since these are probabilities, we only have two states. Does anyone have an idea of a restriction that we might have to place on alpha and beta so that they are actual like probabilities? Yeah,
-1 to 1.
sure. That's true. I guess it can't be negative, right? It's a probability. So it's gonna be at least it's gonna be between 0 and 1, but that's a good start. And then does anybody else have an idea? Okay, so basically since these, yeah, sure. Yeah. But since there are only two options, 0 and 1, we need the probabilities to sum up to 1, right? Like something is going to happen. It's either going to be 0 or 1. So we're going to have this condition. And so we can refer to this as maybe like a sort of normalization of our state. And I realize my handwriting might be bad, but let me know if you can't read it at any time. So does this make sense to everybody? This sort of condition, why they're like that they are probabilities, we need them to sum up to 1. Okay. So again, once you perform this measurement and you get a you get a state with some probability, it's going to sort of collapse to that state. So you can imagine that we maybe started with this state on the top right, and again, with these rules, you have these probabilities of transitioning into 0 or 1, and this is sort of known as collapse, if you've heard about that in quantum mechanics. And after that, let's say like this happened, so we got the state 0. Afterwards, our state is going to transition into some sort of like psi prime. I'm just going to say the state after measurement is just going to be equal to 0. So this is different from classical like computing, right? Where if you perform repeated measurements, the first one is probabilistic, but after that, you're going to keep on getting 0, and you've also changed your state, right? So maybe we were in some sort of superposition is what it's called when alpha and beta are like not they're both like non-zero, and then now we've sort of gone into this deterministic classical state, right? Where we can keep on measuring, we're just going to keep on getting 0 out because you can imagine this is like a 1 in front of the 0. And so since alpha equals 1, we're going to have like the probability of measuring 0 out is just 1 squared or 1, right? So we're always going to get 0 now. Does this make sense to everybody? Like the state and how we measure it and what happens after measurement? Okay. Yeah, so maybe a quick recap for you. All we've really talked about so far is that we have a qubit or quantum bit, and it's described by this state over here on the top right. And so we have this like 0, this 1 that just represent the 0 and 1 states. We have these coefficients, and the probability of measuring them is given by the coefficient squared. And after that, it collapses to what you measured. So this will sort of irreversibly go back to a 0 or a 1. So moving on. Of course, I've talked about these states being 0 and 1, but that's quite abstract. So to make it a bit more concrete, we can put them into a vector form. So we can go from the ket to a vector, and this is basically the rule where we're going to have the 0 state just go into the 1, 0 vector, and the 1 state go into a 0, 1 vector. So also just to maybe gauge everyone's experience with basic linear algebra, like does everybody roughly know what a vector, a column vector is, and a matrix is? Like maybe raise your hand if you don't know. Okay, great. So I'm gonna proceed with some knowledge, a very basic linear algebra. Just stop me if you don't know it. So yeah. Moving on to how we might represent a general state using this vector formalism. Recall that this is our general state, and we just have this restriction where alpha squared plus beta squared equals 1. And let's just sort of plug in what we know about the representations of the kets as vectors. So here we're just going to plug in what we know the 0 is, which is this, and what the 1 is, which is that. And then they're just, again, these are normal coefficients, alpha and beta. Again, I said we can just imagine them to be any real number right now. So it's like 1/2, 1, negative 0.25, whatever you want. So we just multiply it out here, and then we're going to add it up like this. And so this will be sort of the representation of this abstract ket. And so you can kind of see, as says here, that you can read it, you can sort of transfer it back by seeing that the top number in your vector is the coefficient of the zero state and the bottom is the coefficient of the one state. So like as an example of this, let's say we have some other state like 0.8, 0 plus 0.61. So can anyone tell me like what this looks like as a vector? Just using this rule where is this legible by the way, or okay. Sorry guys. Yeah.
Be 0.8 on the top and 0.6 on.
Yeah, exactly. So this is something we'll do throughout where maybe we'll work with this more abstract notation and we'll see why it has benefits later, but for now you're just gonna have to kind of like, I guess this comes also a bit, yeah, Ian?
I just wanted to say that like you can take notes, that's perfectly fine, but we will also release these slides exactly as they are, like after the lesson, so you guys have access to them.
Yeah.
Why'd you write 0.8107 plus 0.6117?
Yes. So again, I was just adding in this, the bracket around it. So yeah, in general, as I was saying, we'll mostly be working abstractly to describe quantum algorithms with this weird ket notation, but then to make it a bit more concrete and actually compute on it, we might transition to vectors and matrices to perform that. Does that make sense to everyone? Okay. So yeah, I guess here's another practice example. Maybe somebody else, if you can tell me what this looks like as a vector.
1 over 3
Mhm.
is often read under the
Yeah, exactly. So just a very simple rule. And again, this corresponds to the 0 coefficient. This corresponds to the 1 coefficient. Okay. So yeah. So again, as I said, these are called kets. So these are the ones with a sort of slanted line on the right, and they have the straight on the left. But we also have this thing called bra, and this is, I guess, a bit more like extra knowledge. So I'm just going to put like this symbol here, where like you don't really need to know this, but it'll come up sometimes in what we're talking about. So like if you get it, that's good. If you don't, like don't worry about it too much. So the bra is basically a row vector, right? So column vector ket. So this is column vector, and this is row. And so how you get it is you just take a transpose, right? So you kind of like lay it on its side almost. So if you have something that's like alpha beta, you're gonna move it into like a row version of the same thing, right? So there's one more detail where technically you have to take the complex conjugate as well, but right now we'll just work with real numbers, so you can also like roughly ignore that for now. But again, ket, column vector, bra, row vector. So since I guess we'll assume some basic knowledge of linear algebra, one fact about these states, yeah.
Why'd the two names get reversed on top?
Yeah, I think
Yeah.
this is a older version of the slides that weren't fixed, but yeah, good notice. So with these states, we can represent sort of their inner product, which is saying like how much is the component of one against the other. I guess from basic linear algebra, you have your dot product, right? Where you can do like A dot B. And more abstractly, we're just going to represent this as like this notation, where we're kind of putting the bra and the ket just next to each other. And since, again, some knowledge of linear algebra, this basically just represents when you plug it in, the multiplication of a row vector with a column vector. And since, you go like across the row and across the column to compute this either vector product or like dot product, you'll find that it's like 1 times 0 plus 0 times 1 or 0. So basically their inner product or their dot product is 0. And one thing that you can call this is that the states are orthogonal. So I guess if you remember from linear algebra, the dot product is their magnitudes times their cosine of the angle between them. So if they're orthogonal, that means that the cosine goes to 0. So they're like 90 degrees apart, right? So yeah. This is a fact that we'll make use of as we begin to like develop, I guess, like matrices and how they might act on kets. And it'll be useful to know that these are orthogonal states. So whenever we see like some expansion that includes terms like this, we can just like cross it out to 0, right? So the state's orthogonal. And same thing for 1 and 0. Now, one more fact is that if we take the inner product of a state with itself, we're just gonna get back 1. So I'm not gonna go through it again for the sake of time, but you just convert them into row and column vectors, carry out the basic dot product or multiplication, and you'll get back a 1. And actually what this reflects is that they're normalized in probability, right? So you can imagine that we have our alpha beta and our alpha beta. So this is like the inner product of a state with itself. And when we take the product, we're gonna get alpha squared plus beta squared. And since we're requiring it to be 1, this is just a reflection that they represent probabilities, right? That makes sense, everyone? Okay, so again, this is our general quantum state. And this is also a bit extra knowledge, but I guess if you're curious about more of the math or the background, I'll just quickly run through this. But you can formalize this measurement process more properly by considering an inner product or a dot product. And again, these are, for our purposes, analogous. So I guess like inner product is going to be like exchangeable with dot product. So if I refer to it as inner product, you can just imagine dot product from basic linear algebra for like real numbers. So with this, again, this notation represents the dot product with inner product. And when we expand it by plugging in the state, we're going to get this. And now we can, since basically they're just like constants and vectors, we can kind of flip around the order of constants. So we can pull this alpha out and we can pull this beta out. And what do you guys notice about these remaining inner products from what we've talked about earlier? Yeah. Yeah,
And be 1 and 1 would be 0.
exactly. So the first one reduces to 1, second one to 0, and just continuing the simple calculation, you just get alpha squared. And so this is, you can imagine it's kind of like a derivation of the rule I said earlier, where the probability of getting a 0 is alpha squared. But of course, if you take that, then you might be wondering like, why is this the real expression? But this has to wait for maybe like a real quantum mechanics course. So for our purposes, you can really just like take this rule, just remember it, and that'll be all we need for our purposes. So pretty simple rule. And again, by doing the same process, the 0 will just flip in both of these. And so this will flip from a 0 to a 1 and vice versa, and you'll get beta squared out. But again, this is not too important for us. So, okay. I get that the so the answer is here, but does everyone get why the probability of measuring a 1 in this case is 4/5? Anyone have a question about this? So just for one more example, so I'm gonna have maybe 2 questions about this. So one, I want to ask, what is the probability of getting a 1 in this case?
Is that valid state?
Yeah, so that's gonna be my second question. So this is technically not a valid state, right? Because if you square alpha and beta, you're not going to get 1. So technically these can't correspond to probabilities, but let's assume it's normalized. Okay, let's ignore that. So what is the probability of getting a 1 here? Just using the rules we have from earlier, where you take the coefficient and you square it.
25/36.
Yeah, so that's pretty much all we need to know for our purposes. Okay, so now again, the goal of this is we're trying to build up to quantum computing, right? So of course we can't just describe 1 bit at a time or 1 qubit at a time. You can't do anything with just 1 qubit. So to sort of expand our collection of states, we're going to use this thing called the tensor product, which maybe has a scary name, but for us, all it really means is that you maybe have one system. So you maybe have like your psi1, just one state. And you can imagine maybe it's like some sort of cloud. It's just some system. And then you have psi2, and it's another sort of system. And their tensor product, which we're going to notate with this times and a circle around it, is basically just like saying, okay, I'm just going to consider like all of it at once. And this is our like sort of quantum state. And that's basically all you need to know for our purpose. It's like saying, like I have this apple, I have a banana, I tensor product them, and now I have an apple and a banana. It's sort of like what I'm considering. So it really doesn't mean too much for us right now. So this is some notation. Again, we're gonna use this times with a circle around it. And since we're all lazy, a lot of times we won't write it. We'll just understand they correspond to different systems. So you might also see a subscript here. since like, maybe this psi is coming from system one, this phi is coming from system two. And since we are really, really lazy, we don't want to write all these extra symbols in the middle. We might even just write it like this, okay? We just have like sci-fi in a ket. And so one way that this maybe becomes more tangible is, let's say like, I have a 0 in my state and Ian has a 1. And so when we want to consider like what we have together, we're just going to tensor it. And some order is going to be assumed. So let's say like I'm going to go in the like left position, Ian's going to go in the second position. So as we tensor them, just some shorthand as illustrated above, this is going to be just written like this. And so you can, whatever, read this maybe as like ket 0, 1, or the fact that like I have a 0, Ian has a 1, right? So that's how you might read this. So does anybody have a question with this notation of a tensor product?
This case like does matter.
Yeah, order it does matter. Again, it kind of refers to maybe like two systems. So of course, like if I have a 1 and you have a 0, that's different from vice versa, right? So that will be important for later on. And we'll see an example right now, actually. So let's consider two general quantum states, right? So maybe I have this state psi, and Ian has state phi. So this is Ian's, this is mine. And we want to consider like what do we have as a whole. So again, we're just using this notation for what we have, and we're just going to tensor product them together, right? And the tensor product is a sort of linear operation, which means that you can kind of like imagine it as some sort of multiplication. That's why this notation is maybe suggestive. So we can basically do what you might normally do, which is like you just multiply each component of the first item with each of the second. So if we take the first out of each one, this alpha 0 and gamma 0, we're going to get this first term. If we take the alpha and multiply it with this term, we're going to get this one, and just so on and so forth. So we get all these terms, right? Does this make sense? Just this simple expansion?
It's similar to like boiling, I guess.
Yeah, it's basically just imagine it as multiplication. But of course, again, you can't switch the order as you asked earlier. So as we'll see here, when you begin expanding it, you want to make sure that you keep the order of your kets that you had. So since here, like for example, in this one, we got it from the alpha 0 on the left and the delta 1 on the right. We cannot write it as like alpha 1 tensor delta 0, right? This is a different state. Does that make sense? So when we begin expanding this out, as on the bottom, again, we can sort of pull constants out because we have like constants, we have vectors. The constants kind of commute through everything, and the commuting means that order doesn't matter. So we can just pull them all the way up to the front. So that's what we've done here. And finally, again, using our notational shorthand, we are lazy. So we're not going to write any of these tensor product symbols. And so our final thing will just be this. Does that make sense? Okay. So again, to read this out, the first term basically says that, in this case, I have a 0, Ian has a 0. In the second case, I have a 0, Ian has a 1, and so on. So as a generalization of the sort of probability rule we mentioned earlier, which only applied to 1 qubit, now it'll just be like the probability of measuring any state when you measure it will just be the coefficient of that state squared. So now we have 4 states, and let's say we consider the one that I've highlighted. The probability of measuring this will just be like beta squared, delta squared, right? Like whatever. So if we also want to make this a bit more concrete again, by going into the matrix or vector notation, we can just consider the sort of tensor product of these vectors. So this is also going to be called the Kronecker product. And yeah, I know my handwriting is bad, but this will be referenced in the workshop later on. So if you see Kronecker product, it's basically just saying like, okay, we have a tensor product, but we're going to look at their sort of representations on vectors. And so how do we take the tensor product of vectors? It's just called the Kronecker product. So yeah, new name, basically same thing. So how do you actually take this Kronecker product? Well, you're going to take sort of whatever matrix or vector you have on the left, and you're going to first like just, write it with some extra room. And then for each component in that, you're just going to multiply it by the matrix or vector that is on the right. So we're going to have like this. And of course, this is like maybe slightly in a Beeson notation because you have like vectors and vectors, but you compute this, and then I believe it's on the next slide. We're just going to sort of do it component by component, right? So this kind of becomes like the vector alpha, gamma, alpha, delta. This is beta, gamma, beta, delta. And so just dropping these inner brackets, we get this. And so again, you'll notice that it is like easy to convert back and forth without actually doing this Kronecker product. So you can basically see that the top one again corresponds to 0, 0, the next one 0, 1, 1, 0, and 1, 1. So it kind of increases in your typical like binary order, right? Where like 0, 0 is the smallest number, then 0, 1 is higher, 1, 0 is higher, 1, 1. So kind of read it down like that. So again, one thing that might be important for us later on is that the left qubits value is sort of the most significant bit, right? Just like in normal counting, when we count up, the left value is like whatever, has the largest power of 10 corresponding to it. So does it make sense to everyone? The tensor product, Kronecker product? Okay. So just one quick practice. How would you represent this in vector form? You find
So the first one would be 2 divided by square root of 15,
Mhm.
and then the next one's actually missing, so it'd just be 0.
Mhm.
And then you just continued the 3 over square root of 15, square root 2 over 15.
Yeah. So I want to highlight what you noticed, which is since the 0, 1 component is missing, it has a coefficient of 0. So yeah, good catch. And this is the state. And as a quick check, you can see that it's normalized because we have like 4 plus 9 plus 2 over 15 is the sum when you square everything and add it together. And this is just 1. So it's normalized. It's a real state. Okay. So yeah. Now let's consider this 2-qubit state. So again, this is like a general 2-qubit state where we have all the possible basis vectors, or in basis vectors, I just mean like these states, and this is every possible one when you have 2 qubits. And you might also hear them referred to as computational, like maybe like states or like basis states. So like computational states is, yeah.
So if you're given a general 2-qubit state, are you always able to separate into 2 separate qubits that you would have?
That's a great question. So we'll see that later, but the answer is like no. So sometimes their states can sort of become interrelated, and that's called entanglement, which is we might have heard of. So let's consider measuring this. I'm also going to just speed up a little bit now, if that's okay. So you guys can tell me if I need to slow down, but we do have, I think, quite a few slides to get through. So I will pick up the pace a little bit. So let's consider measuring the first qubit now. And basically, we can either get a 0 or 1, of course, and we can get a 0 with probability alpha squared plus beta squared because, well, which are the states that will yield a 0 when we measure it in the first qubit? It'll be the first two, right? And so the probability of getting the first one is alpha squared, getting second one is beta squared. We just sum them. That's the total probability that we get a 0 in the first one. So get this. And analogously, for getting a 1 in the first qubit, it's going to be gamma squared plus delta squared, right? Like this. This makes sense for everyone. It is a bit more nuanced because now, we're only considering 1 qubit measurements in a 2-qubit state, but I hope it still makes sense. Okay, so now one detail, again, this is maybe a little bit extra knowledge, not gonna really ever come up after this, but just for the sake of completeness, let's say we got a 1, right? So that means it must have been like this one or this one that we like measured it from. So basically, we could not have gotten any of these if we measured a 1 on the second qubit. So we're going to take this. This is kind of our new state because when we measure a 1 on the first qubit, it doesn't actually tell us if it's this first one with a gamma coefficient or if it's the second one with the delta coefficient, right? We can't distinguish them from our measurement. So we're just going to say like, it's sort of preserved. Like we have sort of narrowed it down that it's collapsed into these states, but it's not collapsed any further, right? It's not one particular state still. So this is just a normalization factor to ensure that we have the probability still summing up to 1. Because, if this was our state alone, and you kind of ignore this normalization, it would be, this might be less than 1, potentially, right? Because originally in the first case, alpha squared plus beta squared equals 1. And so this might not be normalized. So that's where the first factor comes from. If it doesn't make sense, don't worry, but yeah, just have it there for completeness. So again, since this is our resulting state, and measure the second qubit, its state is not yet fully defined, right? It could be either a 0 or 1. And so I guess that's some of the nuance of quantum computing, where the state that you have in the beginning can be like, it can be described by many, many amplitudes, right? So maybe like a quick, I don't know, jump away from the content in the slide. I'll just write at the bottom here. So if we have like n qubits, so let's say n qubits, we can basically have any possible state with like n binary values here, right? So it could be like 0, 0, 0. It could be like 1, 0, 0, 1, 0, 1, in any of these. So since in each slot we have two choices of if it's a 0 or 1, there are 2 to the n possible states, right? Does this make sense, everyone? And so that means to describe it, you need this many states and coefficients, which means that to describe a general quantum state, it actually grows sort of like exponentially in how many like numbers you need to describe it. And basically in the middle of a computation, your state might be this massive thing. And as you measure it, it starts to collapse down and down. So this is maybe a mental picture you can start to build of what this quantum computation looks like. Okay, let's maybe return to the normal content. So with this example, can anyone tell me what the probability of measuring a 0 on the second qubit is? Yeah, so it's going to be just doing the squares out. It's going to be this plus this, right? 15 over 25, 3/5, right? Make sense, everyone? Feel free to ask if it doesn't make sense. So yeah, just 3/5. So now let's ignore the renormalization we have to perform. After this measurement, what is the resulting state? Can anyone tell me that? So you can just carry over the coefficients. I'm not going to bother you to have you divide by the whatever factor that we had earlier. Yeah.
Over root 15 and 11 and a root 11 over root 15.
Yeah, pretty much. So you just have to make sure that you keep the old denominator, right? Yeah, I see where you're coming from, where you're maybe trying to already renormalize it. But I guess for the KSAT discussion, let's just say like, ignore normalization. It's going to be this with a 0 plus this with a 1. And so these come from these, right? Where we kind of condition on the second qubit being a 0 state. Does that make sense, everyone? Okay, so this got normalized, so that's why it looks ugly. That's why I didn't want you guys to do that. Okay, so now going back to your question earlier of like, can you always separate it out into two qubit states that originally like, you tensor together to form this? Well, let's look at this. So here we have the 0, 0 and 1, 1 states, and their amplitudes are both 1 over root 2. So if we're going to measure them collectively, the probability of measuring 0, 0 is 1/2, 1, 1 is also 1/2. So let's say we measure the first qubit. And if we get a 0, then the only thing that could come from is from this first state, right? And so that means that our 2-qubit state sort of collapses this. And that means that the second qubit has now also become a 0, even though we didn't do anything to it, right? We didn't like apply any operation, we didn't measure it, but we know what it is now. And so additionally, if we do it with a 1, so let's say we measured the first qubit, we got a 1, it could only come from this, and so now the state is 1, 1. So again, the second qubit, we know what it is, even though we didn't do anything to it. So again, just to recap that, like when I said it loud, it's here. And we now call these states entangled. So this is only going to be like I guess, informal definition, which is like, maybe measuring one state will like tell you something about the rest. That's not like, a technical definition you can work with, but maybe just for a bit of intuition, that's what you can think of. And more technically, like more properly, and going back to your question from earlier, a 2-qubit state is entangled if it cannot be expressed as the tensor product of two states. And one way to intuit that is if it was the tensor product of two states, it's kind of like they're already separated, right? You have like one state living on its own, and it's been tensored with another state on its own. So they're like kind of disconnected. But since So you can find a simple proof online of why you cannot express this as the tensor product of two states. And that, goes back to why it's entangled. They kind of like don't exist separately in their states. There's some like reason that they're like intercorrelated. So yeah, just some like hand wavy intuition, I guess. Okay, so let's say we did this. I guess you guys can read it. And what can you say about the first qubit? Yeah,
Those are the questions. So when they're ordered as like one, let's just look at the middle one, it's big
Sure.
1, 0. The
Mhm.
second qubit would be the 0.
yeah,
Um,
exactly. Or I guess, yeah, sure.
The first qubit would also be 1.
Yeah, exactly. Since it can only come from this state. And so in this state, the first qubit is 1. Okay, so now we've kind of talked about our states, how we build them up, how we build them up for multiple qubits. But of course, this is computation. We need to actually act on them somehow. So to do that, we have quantum gates. So one funny feature of quantum is that since it has to be reversible, sort of coming from quantum physics, but we're just going to take this as a fact, all the gates are reversible, which means that we're going to see that we can represent these gates as matrices, and they have to be invertible matrices is sort of the point of this. And again, as we apply these gates, since our state has a probability interpretation, it still has to, after applying whatever gates, it's going to have to still sum up to 1, all the probabilities. So these are some more technical conditions. You don't need to worry about them too much. One other thing is gates can act on multiple qubits. So you can have like a 2-qubit gate, 3-qubit gate, so on and so forth. And this is definitely the most important fact out of these, is that gates are linear. So this comes from the fact that they're sort of based out of linear algebra. All the operations in linear algebra are linear. And that means that, let's say we have this operation or this gate U acting on this general state. Well, since it's linear, it kind of distributes. So we have, I guess, one intermediate step that's not written is it's kind of like U of alpha 1 plus U of beta 1, right? Distributes out. And again, we can pull the constants out since they're just constants like 1 or 0. And so that's why we get this. So what this means is even on a completely general state, such as we have on the left, all you need to characterize its action is what it does to the basis states. And so this is actually a fact just from linear algebra, but it'll be useful for us in that like we can describe what it does to the 0 and 1 state, and that tells us everything about what it might do, just by the fact that we can sort of factor, it out, as shown here. Does that make sense, everyone? This is quite an important concept, this linearity. Okay. So again, since our states are vectors, when act on vectors, well, they're matrices, so these gates will be represented as matrices. This unitary is a consequence of the fact from earlier that they have to be reversible and they have to preserve probability. It's just some like, definition from math or physics that we don't need to worry about, but you can, if you hear a unitary matrix, that's a matrix that can act on our states. It's what you can interpret it as. And so these are the gates we're going to look at here. So we're going to look at X, Z, H, C naught, and Toffoli. So we'll talk about what that is right now. But before we get there, just to talk about how we'll represent all these states, I guess, yeah, these qubits and then how we act on them is just like how classically we have these sort of input bits, intermediate bits, and output bits, and they're sort of represented by lines going through. And then you act on them with gates such as AND or NAND, whatever. We're going to do the same thing in quantum where we have our input qubits. So you read this left to right. So this is sort of like a time axis or just like, order of what you're doing axis. And you have your qubits. This is, by the way, from Qiskit, which is a software from IBM, Qiskit. And we're going to be using this software to sort of simulate program quantum computers starting next week. But for now, we're going to be using some sort of a classical simulator that Ian will talk about. So we have this. These are some gates, how they might be represented by these H's. This is a 2-qubit gate, as how it acts across multiple. And this is a measurement, as we talked about earlier. So when you measure it out, you sort of store it onto a classical register, and that's what this means. Yeah.
Is it possible to have complex numbers in gate circuits or gate matrices?
Yeah. And so that's a consequence of the fact that our state can also be complex, but for now, that's not important to us.
Wait,
Uh,
that doesn't make a lot of sense.
so, okay, I guess I can briefly talk about it since now it's come up. So before we've talked about, we have our alpha 0 plus beta 1, and you square the coefficients. But you might have noticed I didn't just write the square, I wrote this sort of norm squared, or like, absolute value squared. And so this comes from the fact that they can be complex. So maybe we have some sort of like I, right? And so we have I is the square root of -1, I 0 plus minus I 1. And so I guess this isn't normalized. So you have this. And again, the probability of measuring at the 0 is I over root 2, the norm squared. Uh, you know, does everybody have some familiarity with complex numbers? Maybe raise your hand if you don't. But yeah, then so the norm of this squared is 1/2, right? Okay, but since our states can have complex coefficients, the operators on them can also have complex numbers inside. So this is our, going back to the gates. So yeah, this is from Zoom. So Dhruv, it's not going to be -1/2 because we're going to take it sort of like norm or absolute value squared. We're basically just taking the length of this number in the complex plane. And so, yeah, okay. So this gate, the X gate, another name for it, like I guess going back to what it does, is you can kind of think it as like a quantum NOT gate, and it just flips between 0 and 1, and that's what the NOT gate classically does, right? So a representation of it as a matrix is this. I think we have an example here. So again, going back to the circuit model, we represent the incoming on the left with this qubit. Its incoming state is 0. We act on it with an X gate, and we're going to get it with this 1. It's just so this comes from its definition, which you can just memorize, right? X is like a knot. But just to see it sort of in matrix and vector mechanics, so matrices act on the left of vectors, right? From linear algebra. So that's why the order looks a bit flipped here. So we have our starting state on the right, we have our matrix. And if you perform the multiplication, you get this like this times this is 0, this dotted with this is 1, and this is our 1 basis state, right? So this is ket 1. And so this is basically saying that x times 0 is 1. And you can do the same thing for the other case where you're starting with a 1 and you get out 0. So one useful thing from linear algebra that I'm just going to talk about that you can use is the columns of a matrix actually give you the result of what happens when you act on that basis vector with the matrix. So to make this concrete, let's say you have like alpha, beta, gamma, delta, and it's acting on 1, 0. If you just perform the multiplication, you're going to get alpha, gamma, and this is the first column, right? And if you do it with 0, 1, you're going to get beta, delta, and this is the second column. So basically, you can also read out what a gate does in its matrix form from the rows, right? So it's saying that 0 will go into this 0, 1 vector, and we know the 0, 1 vector is the 1 ket representation as a vector. So it's saying 0 goes to 1, and here the second column is saying that 1 goes to 0. Okay. So direct message during each gate. So I guess, yes, maybe so the question was like during each gate, do we calculate the probability of whether it's 0 or 1? You don't really calculate the probability, but you're sort of tracking the state ket or the ket, the vector, whatever you want to call it, throughout. And from the ket, you could, of course, tell the probability if you were to measure it, but you're not going to directly measure it. You can, the probability is sort of encapsulated in the state, right? As we know from before. I hope that answers your question. Moving on. So yeah, again, by linearity, if you have x acting on an arbitrary state, it sort of like goes, you can expand it out like this, and then x acting on 0 flips it, 1 flips it, so you get this out. And you should be able to, even at this point, just like see this without doing this intermediate step. Just, from like linearity and like what it does to basis states. Yeah, you can, I guess, does this like sort of computation make sense? Yeah.
Just thinking about this, like if you take the norm before squaring in your probability calculation, then what is the difference between like 1 over root 2, 1 over root 2 is a state at negative 1 over root 2, negative 1 over root 2.
Yeah.
The negative goes away, right? What's the
Yeah,
difference?
so that's only for the probability, but there are, of course, like effects. You can kind of like, I'm not gonna go into the details right now, but like hand wavelength, you can think of it as like quantum interference, where maybe like when you add, I think we'll also see an example of this later when we get to the H gate, but since they can be negative and positive, they can actually cancel out. And so that means that before you might have some probability of measuring a zero and some probability of measuring a zero. When you add them up, that amplitude of measuring a zero might cancel out because maybe you have like minus 1 over root 2 and plus 1 over root 2. So you add these states up, now you have a zero. So even though there was some probability of measuring them before, after you do this addition, there's no probability, which is pretty weird. Because like classically, if there's like some chance I get an apple and some chance I get an apple in another case, like I consider them as a whole, like there's still some chance I get an apple, whatever, right? So, but in quantum, it can sort of like destructively interfere. Yeah.
Right, so it's just, isn't it just, it's like, if you're comparing a qubit that's in like 1 over root 2, 1 over root 2, and one that's in negative 1 over root 2, negative 1 over root 2, it's like, they're the same if you're gonna measure them immediately, but they might be different after you apply a gate to them.
Yeah, exactly. Uh,
There is, but it comes from physics. It's called a Pauli X gate, and then we also refer to it as a NOT gate because of the effect on the 1 0 and then the 0 1.
I think he probably can't hear you actually because the mic is here. But real quick, it's the Poly XK if you want to Google that. I think I won't talk much more about it for the sake of time. You can ask us about it afterwards. So going on to the next gate, we have Z, which leaves 0 unchanged, but it multiplies 1 by -1. And so what this means, it doesn't mean that it goes to -1, right? This is not a state, but it means that the coefficient gets multiplied by -1. So we have maybe like this is what it does. So its action is like this. And again, you can maybe read it out by like, what does it do to the 0 state? It brings it to 1, 0, which is the 0 state. And what does it do to the 1 state? Well, it brings it to 0, -1. And again, this is from reading the columns as I talked about. And this is negative the 1 state. Okay. So if you want to just do some computation, you can verify that this matrix acting on what we have defined to be our state vectors does what I said it does, which is like, this top line. But I won't go into it right now. It's just some basic matrix multiplication. Okay, and then again, by linearity, this is another, right? So if we have Z acting on our general state, when it goes onto, when it acts on the 0 ket, it doesn't do anything. But when it acts on the 1 ket, it flips the phase. So you get this alpha minus beta. And so again, going back to your question earlier, this is a different state. Even though if we measure it, we'll get the same statistics, right? The probabilities don't change, but we'll see next week how you can visualize these states, and you'll see that it is a different state. And if you do other operations to it, it is different. So now for a very important gate, we have the H gate. And so its full name is Hadamard, but this is too long to, put in a box and write on our circuit diagram. So it's just H for us. And this generates superposition, which basically means it takes a state which has a definite state, which is like, if you measure it, it's definitely a 0 or 1, and it can put it into a state that has some probability of being in either. And I guess I never properly defined it. I honestly don't think people do vigorously define this concept, but it just has like some probability of being measured into multiple states. It's superposition, right? It can be this or that or this or that. Yeah, question?
Is Hadamard the name of the guy who made the game?
Yeah. Okay.
Wow,
So
narcissistic as fuck.
okay, this is what the H gate does, as maybe just one more thing to memorize. I promise there won't be much more. So this is just one thing. If you do any quantum, it'll just be like one basic thing that you should probably memorize. So the 0 state goes into the superposition of 0 and 1, while the 1 state goes into another equal superposition, but there's just a flipped phase, right? And if we want to just write as a matrix, it looks like this, which you can confirm again by doing this column vector approach I talked about earlier, where it kind of tells you, okay, we have a root 1 over 2 of being in 0, 1 over 2 of being in 1 if we act on 0. And here, like these numbers correspond like this. And then if we want to act on it, I'll just go into this one in a bit more depth just so we get some practice with matrices and vectors. So let's say we feed in the 0 state and we act the Hadamard. So the 0 state we know is this 1, 0 column vector. Hadamard we know is this matrix. So if we perform the multiplication, you can, I guess, do it as, yeah, so this row dotted with this column, and you're gonna get 1 over root 2. And if you do the next one, you also get 1 over root 2. And so you can expand it out as this, and this basically tells you that, 1 over root 2 of being in 0 or 1, as is basically just from this identity up top. And likewise, you can show it for this. So has everything I've been covering up so far, like X, Z, H, does this make sense for everyone? Any questions? Feel free to ask. Okay, so one question is, if we do this gate on multiple qubits, can this cause entanglement? And the answer is no. Entanglement, intuitively, you can think of as like, there's some sort of correlation between qubits. And H only acts on one qubit. So if we just keep on doing like H to different qubits, the qubits aren't really talking to each other. They kind of stay in their separable states where we can still like tensor product them together, which I know might be a lot of words that you've just learned, like just being thrown at you, but the answer is no. We need some sort of like entangling or multi-qubit gate, which is actually going to be very next slide, or right after this, I believe. Okay, so as some quick practice, we're going to just look at what this circuit does, right? So this is like our first step towards a real quantum circuit, real quantum algorithm. We're going to consider like, inputs. We're going to do several operations, and we want to see what is the output. So, okay, I think, yeah, it's not quite walked through right now, so I'll walk through here. After you apply, so again, we read from left to right, and after this first part, can anyone tell me what the resulting state is? If they remember like what H does on the one state? If not, that's okay. This is, okay, so the state after here, we'll say this is psi 1. So psi 1 is 1 over root 2, 0 minus 1, right? Again, it goes into this sort of equal superposition where the probability of measuring a 0, 1 is 1/2, as we know from like, taking the coefficient and squaring it. But it just has this minus sign in front. Okay, now after we apply a z, so let's look at the state here. And we'll call this psi 2. So psi 2 is equal to z psi 1. And just, writing it out, we get this, right? And then we're just going to act via linearity. So this first term, it's 1 over root 2, 0 is unchanged, right? We know z doesn't do anything to that. So we just keep that. And for the next term, acting on 1, it flips the coefficient, right? That's the definition of z. So this becomes like this. So this is the state at this point in the circuit, right? Everybody follow the math I've been doing?
This example's for.
We didn't save it. That version. I think Ian's working on it. Yeah, I looked down. So okay. So now let's look over here. After the full circuit, we have state psi 3, right? So just writing it out, it's going to be x acting on psi 2, right? Because we had this state before, now we just apply the x. And so we have x 1 over root 2, 0 plus 1. Yeah, a lot of parentheses. I hope you guys can either read or okay, I'll write bigger for the next one. So it's 1 over root 2, and then x acting on 0, what does that give us? Yeah, so it gives a 1, flips it. And then x acting on the 1, what does it do? Yeah, so we get this. So what you might notice is actually the x gate didn't do anything, right? This is actually the same state as we had before. We should just flip the order of the 0 and 1. So from linear algebra, you would call this an eigenstate of x, but this is not relevant for us. So just a remark if you're interested. So this is the output state of the circuit. Okay. And this is how you might do a basic calculation. We won't have to do anything like this. We might do some sort of calculations like this to derive some algorithms that we'll see in like a week or two, but you don't need to like be able to do this, but just like understand the process of how it's done, right? That'll be sufficient for us. So yeah, this is the output. And now let's talk about, going back to the question from earlier, how do you create entanglement maybe? So for that, as I referred to, we need some sort of interaction between qubits. So we need this multi-qubit gate. And one very common example of that is this controlled gate. And so the controlled gate is going to be notated like this, with a filled in circle on the what we call control qubit, and it's going to have a gate acting on the target qubit or qubits. So it's possible for like a controlled like multi-qubit interaction, but again, not really relevant for us. So here we're saying the X controls like the U happening on the Y. Or I mean, like you wouldn't read it like that, but that's like how you might interpret this. So how does it actually work? Well, if the control qubit has the value 1, then we're going to apply the operation. So then we're going to apply U to this qubit in register Y. But if the qubit X has the value 0, we're not going to do it, right? So basically, we only apply the controlled operation if the control bit is 1. Does that make sense, everyone? So yeah, just said here. And this enables a conditional logic because, it's like if this, then do this, just like in classical. And we know maybe from like, your guys' experience in like programming that like, if, else if, whatever, like that's like important. So this conditional logic is important for us. And it also enables entanglement because it is a multi-qubit gate. Okay, just as a remark. So an example of what does this circuit do? So yeah, here's the worked example. So again, we're going to feed in a 1 on the top and a 0 on the bottom. And so just how we notate this is that psi1 is equal to 1, 0, right? We read from top to bottom. Okay. Again, order matters. And now we're going to apply an H and then a C naught. So a C naught is equivalent to CX. And again, it's this controlled X operation. So we might notate it as this, acting on 2 registers, or as like this. And so these notations are indistinguishable or like identical. Where this is maybe what we saw on the last slide. We have this control and it controls an X. And this is what it's commonly notated as because this is an extremely common operation. So just some notation to get used to. Now let's walk through the example. So again, this is the starting state, 1, 0. We read from top to bottom. This is the next state where we're going to apply a Hadamard to the top qubit, which means we apply to the left one. And so this is maybe a bit of a nuance where like, you might ask like, how do you notate it? How do you like see what it applies to? But we're just going to like make it clear with these parentheses, right? Another way of notating this is maybe like H on 1. And we haven't done anything to the second qubit. So it's kind of like, this. And just with shorthand, being lazy, we're going to write it as the thing on the left. So now to actually calculate this out, and using what we know, this is what it does to the 1 state, right? Just a rule. And then now we have this tensor product. Again, like here we kind of omitted this tensor product. So it distributes, it's kind of like multiplication as I talked about. So we kind of, have this, which gives rise to this state. And we have this, which gives rise to this state, right? So when you expand it out, you get this. Does it make sense? Yes. And as the last step, so just reminding you guys, this starting state corresponds to when we were here. The state that we just calculated corresponds to just after the application of the Hadamard, but nothing else. And this final state is after the C naught. So we apply the C naught. We're just going to notate it like this. And again, the control bit is the top qubit, and that one is on the left. So we're going to look at if the left state is a 1, we're going to flip the second one, right? Because that's an X, and this is a controlled naught. That makes sense what I just said? So now actually implementing that, well, I guess first by linearity, we're going to sort of distribute it into the parentheses. So now we have this. And then now actually applying it, well, let's look at the first case. So since the first qubit is a 0, we don't do anything, right? The control is sort of like not activated. So it stays as 0, 0. But now in the second one, the first bit is a 1. So we're going to use the control. Like it's going to apply the X to the second qubit. And we know that X on a qubit flips it. So it becomes a 1, 1. So we get this. Okay? This makes sense? So this is our final state after the circuit. And what do we see? So we see that even though we started in this state 1, 0, which is not entangled, right? The states exist on their own. One of them is a 1, one of them is 0. Now we have this entangled state. So I'm not going to prove that it's entangled, but intuitively you can see, if we measure the first qubit, we know the second qubit. If we measure the second, we know the first one. So they have this sort of correlation, and that's the entanglement that we're talking about. And so again, it's the C naught that did the entanglement, because before we applied the C naught, it was still this sort of like separable, not entangled state, but the C naught creates this correlation. just to be a bit hand wavy, give you some intuition, right? Does that make sense? Okay. So just about done with the slides. I know it went a bit longer than expected. I hope that's okay with you guys. But so one final thing that will be relevant for the workshop is that you can have multiple controls. So this will be notated as like multiple black circles with your gate on the bottom. So in this case, the natural generalization is you only apply the U if both of the controls are one, right? So just looking at this truth table, so this is and a truth table, basically from maybe like classical or like digital logic, just refers to like if you put in these inputs, what outputs do you get? That's all the truth table means. So here we say that C1 and C2 are the control bits, and the target is T. And so these are the inputs that we may consider. And you'll see that the output on T, well, first of all, this control operation never changes the control bits, right? It's only like if the control bits are something, we might do something to the target, but we'll never do anything to the control. So we're not going to write their output. Their output is kind of like the same. They don't change. But the target might change. And we see that, in all of these cases, when the first two are not both one, we don't do anything to the target. But in the second case, when both of them are one, we flip the target. So we have the 0 to 1 and 1 to 0. And so this is notated as like CCX or CC naught, where the two C's refer to like the two control bits, right? And one other name is that this is the Toffoli gate. Yeah. Again, I think it's a guy, but that's all. And then now we're gonna do the workshop. So with the gates that we've learned, with the basic like circuit formalism, we're gonna try to implement some classical logic using quantum circuits. So this is gonna be like an AND gate, stuff like that. And I think Ian will take it from here, or
Actually, I think it might be better.
sure. Sounds good.
I think we'll have to migrate to the.
Okay, sure. So I think should I join the Zoom and you make me host and we can keep the Zoom going, or
Might be easier just to like, you make a new. Oh, really? Okay, yeah. Your computer shut down, by the way.
no. Does everyone have their QGrade account made? Again, did you add all of them to the?
I think I did. If they sign up for the general one, the general meeting attendance thing, I should have added you. If you don't have a like access to the QGrade organization or slash like notebook, please let me know. I can add you right now.
Could you add me?
Yeah, of course.
I like both before.
Yeah.
Go into both forms.
If you just give us the email, I can add you like right now from here.
It's AWNUCCI.
Sorry.
NUCCI.
NUCCI.
Yeah, at g.cla.
Okay.
Two.
At, where's the at?
Oh yeah. Sorry, my brain's fried.
And there's just no two.
Oh. AWNUCCI at g.cla.edu, right?
Yep.
Okay. Anyone else?
Could you guys just type it into the
Yeah.
Discord in chat? And
Okay, that'd be easier. Yeah.
H minus. Or one.
I'm not sure. I couldn't change it either. So.
Can you show me where Discord? I should.
Yeah.
Oh yeah, of course. Yeah. Type it as well.
The ACM Discord, you verify if you scroll down, there's a quantum, but there, the chat should be there. Yes, that's exactly right, yeah.
More put into the chat. USB.
The Zoom chat. Okay.
Yeah, the Discord chat.
Okay. Yeah, I have the Discord up.
And then from Zoom, I guess you guys heard us on Zoom. I guess if you guys didn't hear us on Zoom, and you are not in the QGrade, you haven't given us your email through the GM form, then just send your email in Zoom, maybe via like a direct message. That would be great. I should go to afterwards.
The URL, the email has it.
If they're wrong, even.
Oh, yeah, sorry. Go ahead.
Yeah, it's hard for them to navigate to the teaching stuff.
I also posted the URL like in the chat and the announcements.
Mhm.
Okay. I should probably turn this off. Nobody. Should I?
Yeah.
Okay, I figured people don't want to disclose their emails.
But already screen sharing.
Okay. So, yeah, no worries.
That's a different.
No worries.
It's very much. It's
I feel like it take roughly about the same time.
guys in the Discord, Ian in announcements posted a few messages up. There's the URL account.keeper.com. You guys can just launch into that. I think it should bring you to a page where you can then access the course that we have, but if you guys can navigate there, then we can maybe troubleshoot or whatnot.
All right.
Disconnect it or I'll first try.
Yeah. Join the meeting. I'll make you the host. Oh my God. I didn't realize I was still screen sharing. That's fine. Are you in?
Yeah.
Host. Change host.
Are people at the account.keeper.com yet? Yeah, maybe let's just yeah, so from there, you guys can navigate to courses on the top. There's a bar. And then you should be able to see, yeah, we've added you successfully. There's the UCLA ACM Quantum Introductory course.
Yeah.
If you don't see it, that means we haven't added you yet. So then
This is what like the organization looks to.
Not in the Discord. I typed it in.
Okay. I think it might just take a
Okay.
To those of you on Zoom, this is what like Curate kind of looks like. And then under organization, like you should show up here. I think. And then you can access courses by going here, and then the course should be UCLA ACM Quantum Introductory course, and you can launch in QBook to access it. Audio's
I
on.
mean the
Oh.
I got it.
Okay.
you want to switch the
Yeah. I'll log out of the meeting now.